Hello, everyone. Talking now today about Dalton's Law of partial pressure. And Dalton's Law of partial pressure is another version of gas laws. Basically, what it says is that when we add, if different gases are contained in the same container, vessel, the pressures add together. Okay, so perhaps we have a scuba tank. What's the total pressure inside the scuba tank? Well, you have a bunch of O2, you have even more N2. You probably have a little bit of helium in there, I'm assuming. Maybe some argon, maybe, I'm sorry, not helium, but argon. I was thinking of another noble gas. And maybe some other ones. Well, they all add together to give us the total. Okay. Now, that's pretty easy. Just remember that pressures are additive within a container. Now, let's look at when we collect gases by water displacement, nowadays, actually back in the day, they used to collect gases using mercury displacement. Well, we know mercury is relatively toxic to us, so we use water displacement instead. The reason why they use mercury is because mercury releases a very, very few vapors, if any, at room temperature. I'm sure there is some, but moving on. Water actually produces a variable amount of vapors, water vapor, or vapor pressure based on the temperature. Okay, so you can picture, to explain this further, you can picture that as water gets warmer, it releases more vapor, more water vapor. Eventually you get to boiling or near boiling, and it's producing just a ton of vapor off the surface of the liquid. Okay, so the pressure of the water vapor varies per temperature, and we have to look this number up, or it has to be given to us. So the total pressure inside of a system when we collect a gas by water displacement, and I'll show you what I mean by that a little bit in just a second here, is the pressure of our dry gas. Let's say we're collecting dry H2 or hydrogen gas, but we're collecting it over water, so there's a little bit of a pressure from the water vapor, and we have to add those together to get the total, okay, or subtract it out possibly to get the pressure of just the dry gas. So this is collecting a gas by water displacement. You notice before this reaction starts here, this thing is totally filled with water, and we have a tube that snakes up in there, okay? So when this gas starts to be produced, now I'm going to turn on the Bunsen burner, as you can see here. So as the Bunsen burner turns on and heats this stuff, it's going to produce a gas that's going to bubble up. Here's to see the bubbles, and push the water out. It's displacing or pushing the water out of the way. And when you look at this one, this will become totally filled with two gases. Let's say this is H2 being produced, or hydrogen gas. So there's a ton of H2 in here. And you'll have a little bit of H2O, okay? Depending on the pressure of that temperature, the temperature of the water. If it's hot water, you'll have more water vapor. If it's colder water, you'll have less. So again, that's a number that we have to look up, or a number that has to be given to us. So here's a problem. Let's take a look at this. We have a mixture of 6 grams of O2 and 9 grams of CH4. It is placed in a 15-liter vessel at 0 degrees Celsius. And what is the partial pressure of each gas, and what is the total pressure inside the vessel? Okay, so if we have a mixture of 6 grams of O2 and 9 grams of CH4, and we're just putting them in a vessel, we're not reacting it, they want to know what the partial pressure of each gas is, okay? So in order to figure out the partial pressure of each gas, we need to calculate P, okay? So we have pressure, volume, temperature. I think we can do PivNert here, okay? So let's just work with O2. So the first thing we'll do is work with O2. And with partial pressure, we need to solve for pressure. Okay, so PV equals nRT. Of course, let me just work this off to the side, which means we're going to solve for P, which means we need to divide out V. So we're going to have P of O2 is equal to nRT over V. Okay, so moles. We're stuck already. Doing a quick calculation, we got to take our 6 grams of O2, and again, that's 16 times 2 is 32 for the molar mass of O2. Again, we have O2 here. Moles of O2, so 6 divided by 32, let me get that out real quick here. Oopsie, 6 divided by 32 is 0.188. So that's 0.188. Let's plug that into our N here. So 0.188 moles of O2. And we have our R, which is 0.0821 liters atmospheres over K mole. And the temperature, what's our temperature? 0 degrees Celsius, so that's 273. Yes, we have to convert to Kelvin. We can never forget that. And volume, what's our volume? 15 liters, and it's already in liters, so that's cool. Okay? So moles cancel, Kelvin cancels, liters cancel. We're left with the pressure. That's what we want. So let's take 0.188 times 0.0821 liters atmospheres over kmol times 273. Don't forget to press equals and then divide by 15. You end up with 0.280. So our pressure of O2 is 280 atmospheres. Okay, so that's our partial pressure. Again, the question says, what's the partial pressure of each gas? Well, I know the partial pressure of O2. All right, so I'm going to erase that. Actually, I'm going to put that off to the side here, 0.280. Okay, so the P of O2 is 0.280 atm. Okay, so I need to know that because I believe it says, and the total pressure in the vessel. So let's move on to CH4, which is exactly the same process. So the pressure of the CH4 is equal to nRT over V, and we're going to take the 9 grams of CH4, and we're going to divide that by the molar mass, which is 16 grams per mole. So let me just get 9 divided by 16 is 0.563, 0.563 moles times 0.0821, 0.0821 liters atmospheres over kmol. I'm being a little sloppy here, sorry about that. Times the temperature. Again, it's under the same temperature. And there's a different way to solve this, by the way. I'm just doing it the long way just so you guys can see that. In other words, I'm defaulting to the normal conditions you would solve problems. And then also volume, which was 15. Okay, like I said, there is a different way to solve this. You might want to look into that. So, and if you're curious, I can show you. So 0.563 times 0.0821 times 273 divided by 15 is equal to 0.840. Okay, so this is 0.840 atmospheres of CH4 gas, or from the CH4. Okay, so that answers the first question. What is the partial pressure of each gas? And what is the total pressure? I'm just going to add them together. So 0.840 plus 0.280 gives us 1.12 in total pressure. So you just add this plus this, and we end up with 1.12. Let's take a look at this other problem. Now this one looks lengthy, and it is. But now here's how it's actually not as bad as you think, or maybe it is. But what we're going to do here in this problem, I'm not going to go through it. It involves a little bit of stoic. I think it might even be a limiting reactant problem. But also, it is a Dalton's Law of partial pressure problem, okay, where you have to subtract out the 21 torr from the pressure of the that is generated from the total, okay? So so 754 minus 21 and go from there. Okay, again, this is something that I don't think I have time to solve for in class. I'm sorry, I can solve it in class if you want, but on paper, it's a little bit lengthy, so at least on video. So again, if you're curious on this one, that's fine, but that would involve several steps. So moving on, all right, that ends that video. So if you want to come back to this, actually, you know what? I'm not going to end the video there. I think I kept going back and forth. I am going to solve this one, okay? So a sample of solid potassium chloride was heated. There's the equation. The oxygen produced was collected by water displacement. Again, whenever you see this phrase, collected by water displacement, that's Dalton's Law of partial pressure. And that was done at 22 degrees Celsius. The total pressure in the whole system is 754 torr. The volume of gas collected was 0.650 liters, and the vapor pressure of the water was at 22 degrees Celsius is 21 torr. Calculate the pressure of O2 in the gas collected and the mass of KCl in the sample of water that was decomposed. So I thought this was a limiting reactant problem. It's not. Okay, holy cow, where do we start? Well, let's rewrite our equation. So we're going to use this equation up here of 2 KClO3 yields the products. And what I need to do first, it says, is calculate the pressure of O2 in the gas collected. So I just want the pressure here, okay, of that stuff. The problem is there's water in there too because we collected it by water displacement. I already underlined that. So what I need to do is subtract out the total. So the total pressure, let's use Dalton's Law of partial pressure. The total pressure of anything in a system is equal to the pressure of the dry gas. In this case, it's O2, plus the pressure of the water vapor in there per temperature. The total pressure, they tell us, is 754 torr. they're asking us to find the pressure of the oxygen, so that's my X, plus the pressure of the water. It says at 22 degrees Celsius, the pressure is 21 torr. Whoopsie, 21 torr. So all I got to do is subtract out 21. So 754 minus 21 is 733. So that means that the pressure of the O2 is just 733 torr. Now that's an important pressure because I have to now use that pressure in my problems, in this problem, excuse me. So 733 torr. Just so I don't forget that, I better write it off to the side here. So PO2, O2 is 733 torr. Okay, good. Now, the next question says, what's the mass of KClO3? Well, this is gas laws. KClO3 is a solid. Let's take a look at that. This is a solid. So, is this? Should we just throw up our hands and Kinkoff will do it? Okay, all kidding aside. What we need to do is use Pivnert. Use Pivnert. And again, anytime in these videos you want to stop and try to guess what's happening ahead of these problems, do it. But we have to use Pivnert here to solve for moles. Once I get moles, now I can plug into a mole ratio. So it works like this. So if I'm going to solve for moles, that's N is equal to PV over RT. The pressure of our gas, notice I'm using it, it's in torr, but it's in torr. Pressure of O2 is in torr. That's no good. So I got to do a quick conversion, unfortunately. So 733 torr, I got to get this in atmospheres. That 760 torr is equal to 1 atm. So all I got to do is take 733 and divide it by 760, and that gives me an atmospheric pressure of pressure in atmospheres of 0.964. So let's use that. I'm going to erase so it gets out of my way. So 0.964. I'm going to move this down. That's ATM. The volume, let's see, what's it occupying? 0.650 liters. So the whole thing is in 0.650 liters. Remember, gases expand to take the shape of any container, so that works perfectly for us. 0.0821 liters atmospheres over kmol. And a temperature of 21 degrees Celsius, but it's not, 22, but it's not 22. It's actually 295 Kelvin, okay, which I suppose is 22 degrees Celsius, but we had to convert to Kelvin. Cancel out all the happy stuff, or then maybe not happy stuff because it's being canceled, and you ended up with moles. So we have 0.964. Let's find out the moles. 0.964 times 0.650 divided by, start your parentheses, 0.80821 times 295. Don't forget to end the parentheses, and you end up with 0.0259. So we end up with a molar amount of 0.2, what did I say? 0.259 moles of O2, okay? But that's not what the question asks. Again, this was a deep problem here. It says calculate the mass of KClO3. The mass of KClO3. So the mass of KClO3, let's do this. Whoopsie, I went too far. So let's take 0.0259 moles of O2, and let's get KClO3. All right. So we need a mole ratio. This is, by the way, the only way to go from a gas, the only easy way, and I guess it's not that easy, to go from a gas, moles of a gas, to moles of a solid. So anyway, we have 3 to 2 ratio, okay? So 3 moles of O2 to 2 moles of KClO3, okay? That's for mass, so we got to go one more step. Your 1 mole of KClO3, 2 grams of KClO3, and I don't know what that is, so I got to add that up very quickly, and that's 39.1 plus 35.5 plus 48, and you end up with 122.6. I'll plug that in here, and so we have 0.0259. Oh my gosh, this is crazy. Times 2, press equals, divided by 3, press equals, times 122.6, and you end up with 2.12 grams of KClO3. Yeah, that's a beefy problem, guys, but it's a fun one, all right, if you like that kind of thing. So anyway, I just wanted to solve that. I had a few moments. I realized the video has been going on long, so I will cut it off now. I'll see you guys later.